If you've been on the internet at all lately, you've probably seen videos of robot dogs like this popping up more and more. Some cool, some funny, some reminiscent of that one Black Mirror episode. And the comments here are telling about the public's perception of these machines, with one user summing it up for everyone: why are people even making these? And when you learn that these things are now commercially available, and way cheaper than you think they would be, and that anyone can buy one, the slider on that heebie-jeebie scale only goes up. And yes, people are absolutely doing stupid shit with them. But other, more serious people are using them as important research tools. MIT invited me to see two of the Unitree robots they're running experiments with, the Unitree Go 1 and Unitree B1. These bots are the successors of MIT's Mini Cheetah bot and are now being sold at scale. The Unitree Go 1 can run at a maximum speed of 4.7 meters per second, or about 10.5 miles per hour. And it can climb stairs, navigate rocky and even slippery terrain, and can even play soccer. Other robots like the Unitree B1, which is much larger, can carry loads of up to 40 kilograms over rough terrain, and even more for short distances. They can even walk in water. They can be equipped with a robotic arm that can pick up small objects or open doors. And many parts of these robots' bodies are directly inspired from the natural world. For a long time, it was easy to watch robots like this and feel like they're just a human tool. Machines that are cool, but ultimately need us to move around the world, like super neat remote control cars. But things are changing, and robots are being revolutionized with AI. And this is why they are of interest to MIT. The minds of the Unitree robot dogs can be installed with custom programs, so researchers can test different neural networks within these machines. This provides an amazing research platform and makes the robot dogs even more capable than ever before, and possibly more concerning. Robots that once had to be manually programmed by humans are now making their own choices, making complex decisions about the world in real time. Marketing teams are even calling it super AI. There's a lot to unpack here, but luckily for me, I got to see for myself exactly what these robots can do, and also what they can't. So, is this the start of a real-life Black Mirror episode? And what is MIT doing with them? How much are these robots modeled after real animals? And how smart is too smart? The first animal tetrapod came about somewhere around 380 million years ago. It was a fish that evolved legs from fins so that they could walk on land. And this four-legged locomotion really caught on. Today, all amphibians, birds, reptiles, and mammals are considered to be tetrapods. Weirdly, even snakes are considered to be tetrapods because their ancestors used to have legs, which they then lost due to mutations of the Hox gene. They sometimes have vestigial little hind limbs still hidden in their bodies. This is also true for whales. Clearly, there are many ways these four limbs can be used in locomotion: crawling, walking, running, flying, or swimming. So in the late 1800s, when humans started to build moving machines, emulating real creatures' locomotion was an extremely attractive idea. Why invent something that nature has already invented? But as the next decades and centuries would prove, this is easier said than done. The first documented walking mechanism appeared in about 1870 and is called a lambda mechanism. It used rotational motion that translated into a walking motion with a constant velocity, and it could only walk on flat ground. Its four legs were inspired from nature, but the rest doesn't exactly resemble any living animal. The next big attempt to imitate the four-legged locomotion of animals came in the shape of a horse with mechanical legs, powered by the human rider. This is closer to the form of an animal, but it still needed human input. But things only got more amazing from here. Behold the walking truck, built by GE in the 1960s for the US Army as an experimental vehicle for dealing with rough terrain. A human operator would drive the machine by giving commands to each of the legs through a hydraulic system. It could climb over obstacles and kick and push things out of its way, even things like cars. It was a landmark in quadruped technology and in style. But the walking truck was still limited by the humans that drove it. It required human muscles and human thought. It was so hard to control that operators reported being mentally fatigued after just 15 minutes of manually thinking through every leg movement required to get the machine to walk forwards. The need for autonomous robots was becoming clear. So in 1966, the University of Southern California revealed the phony pony. It was the first autonomous quadruped in the US and set the precedent for all of the robotic quadrupeds that were to come. It featured 2 rotary joints per leg, like a hip and a knee, and could perform various gaits like trotting and walking. And since then, the autonomous and quadrupedal tech has exploded. In the decades that followed, there were spider bots, kangaroo bots, and some sprawling crab-like bots. Soon there were cheetah bots, humanoid bots, and now there are many types of robot dogs. The fundamental structure of a quadruped robot typically comprises a body, thighs, shanks, feet, and eyes, or rather, cameras. The Unitree Go 1 has 5 sets of binocular fisheye cameras on its head, chin, sides, and abdomen, which allow it to model the space it passes through in 2D and 3D. And it has 3 sets of hypersonic distance sensors, which allow the robot to recognize and efficiently avoid obstacles and navigate autonomously in complex environments. The legs each have 3 joints, each powered by its own motor. The first joint they call the hip joint, and it's closest to the body and can move the leg laterally up and out. The next joint they call the thigh joint, and it is right next to the hip joint and moves the legs forwards and back. And the third joint they call the calf joint or knee joint, and it similarly allows for a walking motion. The Unitree Go 1's, and in fact many quadruped dogs' back legs are pointed in the opposite direction from a real dog, so all of the robot's knees point in the same direction. This seems a little strange because knees pointing towards each other, as in real dogs, would be more stable. However, robot dogs with knees in this configuration have one major limitation. When going upstairs, their knees collide with the steps, so this isn't an option for their design. But what about going down the stairs? The robots have to do it backwards. Traveling further down the robot's legs, we find its feet, which are spherical rubber balls. This, of course, differs from the complex structure of a dog foot that has toes, digital pads, and claws. But the reason for this difference is simple. A spherical ball is easier to model, simulate, and control. A sphere always makes contact with a flat surface at a single point, regardless of the angle. If you have a flat, complex foot, you have to figure out all of the points making contact with the ground, all of the elements of friction on those points, and all of the ways force is being applied. It's a lot more complex. No one has quite figured out how to do this in robotics yet. But while clearly not as sophisticated as a real dog, the leg design of these robot dogs makes them able to navigate all sorts of difficult terrain. Having 4 legs provides greater stability and balance, because they can always maintain 3 points of contact with the ground. They have independent control over each leg, allowing them to adjust foot placement based on the terrain. And each leg can move in various planes, allowing the robot to step over objects, shift its weight dynamically, or crouch when necessary. This mimics the flexibility seen in real animals. But even though this body design should be ideal for scrambling over rough terrain, programming them to do so is not so simple. To learn more about this problem, I talked to Dr. Pulkit Agrawal, Associate Professor in the Department of Electrical Engineering and Computer Science at MIT, and head of the Improbable AI Lab.
Traditionally, what people would do is they would use their own intuition and some mathematical knowledge, which would be very specific to a particular task, to describe how the different motors should coordinate with each other. So this would take a lot of effort on the part of the human because it really relies on your human intuition to design it. But this approach is not very scalable, in my opinion, because you don't have the same paradigm or the same framework that you can applying to different problems.
On top of this, traditional models rely on having accurate data and can struggle when conditions change too quickly for the model to adjust. So if the terrain is uneven or slippery, traditional predictive models may not be fast or flexible enough to account for unexpected shifts in the environment. However, predictive models and manually programming things aren't the only options anymore. Artificial intelligence seems to be popping up literally everywhere. We have entered the era of deep learning. No one programmed ChatGPT to give me that answer. No scientist predicted every single thing a person could ask it and came up with a bunch of answers.
So what deep learning did, it made this trend happen that instead of people designing rules by hand, we would learn rules from data.
Data. That is how ChatGPT has learned to respond to millions of random questions every day. And that's how robot dogs will be able to learn to navigate their environment. Great. There's one problem though. How do you get enough data? All of ChatGPT's data is based on common crawl data, meaning it's gotten all of its data by scouring the internet for images, books, forums, blogs, and metadata. And it's been absorbing this data for 8 years. But there is no internet of robotic movement, no downloadable library of millions of data points of robots crawling over rocks. Sure, maybe some labs have some data about their specific robots, but there is no robot data that even comes close to the scale of the entire internet. So what's a scientist to do?
So essentially we have to create our own data.
Right.
So how do we create our own data? We let the robot do some sequence of commands. If the sequence of commands are good, we give it high reward. If it is not good, we give it less reward, right? So reinforcement learning essentially is helping us create the data, which is slowly progressing towards the kinds of behaviors that we want to do.
Reinforcement learning. That is the key term here. Reinforcement learning is something you've probably all experienced if you've ever tried to train an animal. Imagine you want to train a dog to play fetch. If you throw a ball and the dog brings it back, you give it a reward, usually food. If it doesn't bring it back, you don't give it a reward. Over time, the dog will learn to do what you're asking it to do. So how does this work with robot dogs instead of actual dogs?
So a big challenge in, making robot dogs do things is that, a robot dog consists of many motors. It has 4 legs, it has a body. You can think about each leg having 3 motors each. So now you need to tell each motor how much should it move so that the dog can, for example, walk, run, jump over the stairs, do other things. So imagine if you just put random commands in each motor, or you moved each leg by a different amount, but without any coordination, then the robot will just fall. Right? It wouldn't fly. So what we need is to find those coordinated set of commands of how to move these motors so that the robot can actually start walking or running or whatever you want it to do. The question becomes, how do we find this coordinated set of movements? And this is where reinforcement learning comes in, where we give a robot dog a reward if the movement patterns which are selected right now lead it to walk. For example, we can reward it based on how fast the robot is walking. If a particular set of motor actions don't lead to walking or lead to slow walking, if you fall down, your velocity is 0, you get no reward. So then we are searching through the space of different combinations till the time we find one which will lead the robot to walk.
But what's a reward for a robot dog? It's not food, but something built into its programming. If it does what the researchers want, like climb a stair or walk forward, for example, it gets rewarded a higher number. But as Gabe Margolis, a PhD student in the Improbable AI lab, explains to me, it can still be tricky to get the robot to do what you want it to do.
For example, if we just give it a reward to walk forward, there's so many different ways that it could walk forward. And how is it going to know which one to pick?
Yeah.
So in practice, when people design these walking controllers, they end up doing a lot of tuning. For example, you might want to say, I want you to walk in the most energy efficient way possible. But well, it's kind of hard to formulate that sometimes using existing methods. And for example, if you put too high of a weighting on energy efficiency, then the robot will prefer to conserve energy over walking, and it'll just stand still. It'll be like, well, I don't want to start trying to walk because I'm just going to use up all my energy. And on the other hand, if you put the energy weighting too low, the robot is going to run. Maybe it's going to learn to run fast, but like when it stands still, it'll also be jittering,
It's just like...
right?
So they're using a different approach. Rather than giving a reward for a specific energy efficiency, their reinforcement algorithm is automatically picking the right weighting for energy efficiency. And they're doing this for other things too, like walking gait.
So the gait usually refers to the order in which the feet are making contact with the ground. So for example, there could be a trotting gait where the diagonal feet alternate. There could be a hopping or pronking gait where all 4 feet go simultaneously. There could be bounding where it like alternates front and back.
Right.
But a lot of the time, if you're using an analytical or classical approach to designing these controllers, you would first make some choice like the robot's going to walk with a trotting gait and then optimize everything around that.
Right.
With reinforcement learning, and particularly with our method that's using a very minimal reward function, it's really not putting constraints on the gait, so the robot's going to do some interesting foot step sequences.
Gotcha. When Gabe refers to the controllers, he's referring to literally the controllers for the robots. They can each be programmed with a different neural network. So now he's going to show me just how different they can be. How hard is it to not like crash into the wall all the time? Because that seems hard.
It is a little bit tricky because this controller, it has a little bit of like drift to the side. And that's another thing that's like reward shaping. It's like, well, how much, I mean, it's going forward, which is what we want, but it's also drifting a little bit. So how much do you want to penalize that?
And now I get to try. This controller is programmed with a minimal reward function, so I can tell it the direction and velocity it should go, and the robot decides everything else. And it's not exactly perfect. Oh, it's sensitive. Oh God. Oh, no, don't hit the wall. Oops. Sorry.
It happens.
It's harder than it looks.
Yeah.
It's like he's got kind of a mind of his own, but also he corrects himself pretty well when I do that. And he wants to fall over.
Yeah.
But he finds his balance, except for when I push him too hard, maybe, like when I made him fall. So when I made him fall, he was going too fast, or like turning too fast.
Especially if you're driving him forward and turning at the same time, because technically, the distribution of commands you can track looks kind of like a diamond. Right. But on the controller, you can command like the whole square that's outside of it.
Gotcha. So
I mean, we can clip it to a range where he will almost never fall, but then you're not going to be able to see like the agile ones.
Right. And where's the fun in that?
I can also show like one other slightly different policy that's like has a lot more reward shaping, might feel more like natural to teleoperate, but it's going to be like less agile, I think.
Yeah, that'd be great just to compare.
Cool contrast.
So this controller is programmed in a way that more precisely tells the robot what they want it to do. In a hallway setting, this feels easier to control. But in a more difficult setting, this robot might struggle to get over things like rocks. I can see how this one's footsteps are more precise. His little tippy taps are like closer together or something.
Yeah.
But the more fluid, chaotic feeling first controller has much more potential for adaptability. And as I play with them, they start to grow on me. Like, he has got personality. Like, I know he doesn't actually, but like he does. Like, it's got personality in the way he wiggles and falls. Like, it's hard to not see it as a dog. A dog with like a weird little 4-eye face.
And a case of the zoomies.
And a case of the zoomies. Clearly, the robots are not a perfect locomotion device. And this is partly because the AI programs within them are still being trained. And as you might be able to surmise, training the robots in real life like this would take a prohibitively long time. Kicking over a robot 10 million times to teach it how to stand back up would not be a good use of you or the robot's time.
Oh, it feels mean, doesn't it? It does feel a little bit mean. Don't hold it against me.
So typically collecting that amount of data by having a real robot function in our environment is not possible. It might take months, years, even beyond that. And the cool thing about robotics is that robotics is all about physical interactions. So we kind of know the rules of physics, which means that instead of a robot collecting data in the real world, we can write down the equations of how those physical interactions are going to be. And that is what a simulator essentially is. It's a digital twin of the real world. And what I mean by digital twin is we are just implementing physics equations. So if the leg hits the ground, this is the amount of force it is going to apply. We can change the friction, we can change the mass. So we can emulate many different kinds of terrains. If we make friction be small, it becomes slip-free. If we increase the friction, it becomes less slip-free. We can have the terrain have some undulations on it, so it can be smooth. It can be as rough as you want. You can have hills, you can have stairs. So you can emulate many different characteristics of the real world. And in simulation, we are not bound by real time, we're just bound by compute. So it turns out, in many cases, in 3 hours worth of simulation, we can collect 100 days worth of data. And the reason this becomes possible is because you can run simulation in parallel. So you can have 4,000, 10,000 simulations running in parallel, which is not really feasible to do with a robot. I'll have to buy 10,000 of them, and then I'll have to take care of them. If one falls down, the motor breaks down, so it's just much more easier.
And that's something that I think has just become possible in the past, less than a decade, and is really one of the driving forces behind why these methods are starting to work, because computers have gotten a lot faster, and the methods for running the simulations fast on those computers have also become optimized.
But of course, if you use simulations, they're an approximation of reality. And there could be a difference between what's been modeled in simulation and the complexities of the real world.
So it could happen that if you train a policy in simulation, it does very well. But because the real world is a bit different from simulation, the policy can fail. And this is what is called a sim-to-real gap. And in the past couple of years, some research from our lab, some research from other labs have pushed this frontier forward, where we have been closing the sim-to-real gap.
And with all of these advances in computing, these robots are becoming capable of some surprising things, like playing soccer. Pulkit and his lab have been programming these robots to dribble a soccer ball, even on variable terrain. A human gives DribbleBot input on direction and velocity. Wide-angle fisheye cameras on the robot perceive the ball. The sensor data and velocity commands are fed into the dribbling policy. And this then tells the joints of the robot what position to be in. And even on difficult terrain, or terrain that changes from grass to tile to sand, DribbleBot has incredible control of the ball. Even if someone else kicks the ball, DribbleBot will redirect itself to go get it.
So this is pretty cute, but why? What's the point? Well, the reason is more practical than it looks.
Walking around and looking at the environment has been a strong point for these robots, but touching the world and interacting with objects has been, I think, a weak point. And so with DribbleBot, really, inspiration was we wanted to take the things that were working in leg locomotion and walking across different terrains and add just like a kernel of object interaction where, okay, now the robot doesn't just need to walk across different terrains, but it also needs to be aware of some object, in this case, the soccer ball, and actually manipulate it to move across the terrain.
So dribbling a soccer ball is a perfect case study for getting these robots to not just walk without falling over, but to interact with their world. Because as fun as these robots are to watch run around, unless they can do things, move objects, push buttons, pull levers, their real-world utility will be limited. And when doing any task like this, one thing the researchers have to include in their programming is something called force control. If their robot needs to pull a lever, they need to be sure that the robot pulls it strong enough to activate, but not so strong it rips it off the wall.
Can you explain the concept of force control in robotics and why that's important?
To preface all of this, our robots are not fully autonomous yet. They're always receiving some instructions from a human or from a high level. So one of the big questions in robotics is how should the human describe to the robot what they want the robot to do? Like there are multiple options. Technically, if I provide some demonstration to a robot of how I'm picking up an object, I might say, robot, I want you to follow the path that my hand took through space. Or I might say, robot, I want you to copy the forces that I applied to the environment. Recently, we've been using some actually like VR headsets.
Oh, cool.
And that technology has actually been really useful for teleoperating robots because those headsets, a lot of them include some kind of like hand tracking features. Like they'll have cameras up on the headset and then they have some built-in software that can track your hand position really accurately. So one way we do it is we can, sort of tell the robot to move its gripper the same way that we're moving our hand.
This is super cool and can be very silly.
Oh my god. Thanks for the ride.
Cool.
But the technology isn't perfect for every scenario.
There we go. No.
And there are still a lot of limitations.
The robot will have all sorts of like constraints that the human doesn't have. For example, maybe I use my hand to pick up some heavy object in a particular way, but because of the robot's like shape and strength of its different motors, it actually can't do that. There's actually sometimes a conflict between, are you going to do like exactly track the position that I took, or are you going to track the force that I applied?
But it's not just locomotion or soccer dribbling that are seeing the benefits from advances in computing power and AI. It's also being used in object manipulation like this. Over time, these robots will be able to do many of the same things humans can do with their hands. The uses of this technology are so vast, it's hard to wrap your head around.
What applications do you hope robots like this could have in the future, in the real world?
That's an excellent question. If I could have a magic wand, there are, infinite applications. I think one of the things we have been recently trying is, could these robots help with search and rescue? The problem is that you have to find people if an earthquake happens. And then people have to carry some equipment to, say, drill holes or, to take out, people if they are stuck. Now, for humans to be in those scenarios, it's dangerous for them. But if robots could help out with that process, that could be quite helpful.
Another important use is monitoring equipment in dangerous settings.
So, for example, if you have a factory or on oil rigs, you might have a lot of old gauges. Someone needs to walk around and look at those gauges and check that equipment every day.
Mm-hmm. And working on an oil rig is dangerous because of fires, explosions, equipment failure, gas leaks, entanglement, or falls, to name a few things. It would be much better for a robot to take these risks than a human. Other things may not appear to be dangerous, but they are.
For example, if you're a warehouse worker, lifting boxes all day in, all day out, it is hurting your back, right? So even those things, where there are health implications which we don't necessarily think about. So yes, we do, imagine a world where these tedious, dangerous things can be done by machines. And we want to provide a tool which enables humans to do what they want to do.
Seems to be in some ways the opposite of some of the AI that's happening right now, like the image generative AI. It's like that's the work people want to do, making art. So it's cool to think about robots that will do the manual labor and the dangerous jobs. What would you say to the people on the internet who see robot dogs and their gut reaction is fear? And to compare it to that one Black Mirror episode, what would you say to the criticism that is inevitable on the internet?
Yeah, and I can completely see where that criticism and where that fear is coming from. I think whenever we are faced with something unknown, some things, which we haven't communicated, why is it what we are doing, there are things that people will induce or think about, right? And in terms of any technology, it's not for the first time that we are experiencing this phenomenon. Perhaps when electricity came out, people were also very afraid that, hey, we can get electrocuted, with electricity. If you think about fire can destroy, but also fire can help us cook our food. Right? So I think with every technology, there is a positive side and there is a way to use the technology which can be harmful. So I think it's the onus of the people who are creating the technology, working in tandem with the society where the technology is going to be used, listening to what their concerns are, working with policymakers to ensure that the technology is being used in a way which is furthering human cause and not trying to compete with humans fundamentally, right?
So with respect to robot dogs, I think people can particularly have this reaction because there's this Black Mirror episode and lots of media that can portray them. But also I think it's just a natural gut reaction to have. When you see something that moves more like an animal, it's easy to assign it a higher level of intelligence or it has some independent thoughts. But I think that gut reaction is definitely a mischaracterization of the technology that I work on. We're not giving these robot dogs a brain like a real dog. We're giving it the ability to walk, but not to make high-level decisions like, I'm gonna go chase something, right? And walking is really just, I think the right way to view it is really just it's an upgraded version of wheels that wheels do, yeah.
Right, and people see wheeled things or robots, and you're right, there isn't that visceral gut reaction, maybe just because we're used to them. Something about the legs triggers that uncanny valley feeling or something. But maybe once these things are more mainstream and they realize that they're not gonna, be weaponized by the military, then they won't be so scary for people.
So we're still very far from a Black Mirror outcome. And as long as the governments of the world do their job, there's nothing to worry about. And we all know how good the government is at doing its job. Realistically, this is just another technology that's a double-edged sword. The advent of cars allowed people to travel farther for work and allowed more time for leisure, and also results in over 1 million road deaths per year. Smartphones and the internet give anyone access to infinite learning and education, and also leads to cyberbullying, sex trafficking, isolation, weird cults, and our collective inability to read a book anymore. The list goes on. Pretty much any technology in our modern world is like this. But with this new robot dog tech, I believe that the good will outweigh the harm, hopefully by an incredible amount. And whether we like it or not, the artificial intelligence revolution is already upon us. It's happening, and it's happening fast. Part of my motivation in making this video is to try to understand these rapid advances. However, as I quickly learned, the scientific literature on things like neural networks and AI can be really hard to parse when you're new to the subject. In some moments, it felt like my brain was going to spontaneously combust. So to help me navigate this subject and finally grasp many of its hard concepts, I used Brilliant. Brilliant is where you learn by doing, with thousands of interactive lessons in math, data analysis, programming, and AI. And their course called Intro to Language Models has been pivotal in my understanding of ChatGPT and this new era of generative AI that seems to have so quickly taken over. Their learning platform is designed to be uniquely effective. Their first principles approach helps you build understanding from the ground up. In the Intro to Language Models course, you begin by inputting a single word into a prompt, which then completes your sentence. Based on the text that comes back, you can quickly understand that this model was trained on one particular corpus, a terms and conditions document. It then guides you through how these corpus texts are used to train language models, and how probability allows the models to know which word comes next. It then explains how the model can become creative, and explains the process of tokenization, something I thought was extremely complicated, but makes a lot of sense when it's broken down into interactive lessons. So with this step-by-step approach, complicated topics like AI and neural networks don't leave you feeling lost and overwhelmed. This learning feels completely attainable. Understanding what's happening under the hood of large language models will be key to navigating the digital world in coming years. And Brilliant's interactive lessons are the most effective, and I would say most fun way to finally wrap your head around it. Each lesson is filled with hands-on problem solving that lets you play with concepts, a method proven to be 6 times more effective than watching lecture videos. Plus, all content on Brilliant is crafted by an award-winning team of teachers and researchers, like professionals from MIT itself. So to try everything Brilliant has to offer for free for a full 30 days, visit brilliant.org/realscience or scan the QR code on screen. Or you can click on the link in the description. You'll also get 20% off an annual premium subscription.